Okay, now it's recorded, and then let me share my screen. Share screen. Here we go. Okay, before the start of the class, I want to mention one thing that I believe all of you have received the email from external evaluator from the project about a survey, maybe. If you have time, please take the survey. Or if you have any questions or feedback regarding the survey, please also let us know. Thank you. Uh, in the last class, one thing here is the Python interpreter here. Let me just open the exercise. I believe there was a NumPy issue that shows something like SDK is wrong or something. Let me see, main maybe. Okay, here we go. So at that time I run the NumPy and it shows something error here. So the method to solve the issue is here. So you can just go to file and then this is what actually an a PyCharm issue. I just click this one, invalidate caches, and I click all of them and now rerun it. Everything's good. It's kind of repaired. And another thing for PyCharm is that sometimes when try to run a code, for PyCharm, a very big problem is the interpreter. So let me see, so you can go to settings and then go to Python interpreter. So what I did was here, so I actually added a new local interpreter. I make it to be here, so that like for example here, you can see for example here, I create like each Python, I create a project with the environment. These two means a Python environment here. So to save my life, what I did finally was I create something here in the folder. I call it PyInterpreter. And for example, if you run some projects, you can you may need to include a lot of folders. You can create an interpreter for PyCharm as well. So in this case, every time whenever you create a new project, you can just name this one as this one as the interpreter instead of choosing everything for a new interpreter. Or if you have already installed Anaconda, as I mentioned, you just choose this one, Anaconda. I believe Anaconda covers most need for those kind of data mining, for those kind of data science. And also, when you need to add a library or package, you can just install here in settings and then project Python interpreter, click plus. For example, if I want to add NumPy, if I want to, sorry, NumPy. So I can find here, for example, NumPy. Actually, I've already added here. So, but if you have not added, just click install package. So here I basically added four things. So the first one is NumPy, and then Matplotlib, and also the scikit-learn, sklearn. Where the scikit-learn? Let me see here. Be careful, the scikit-learn. You need to add a scikit-learn instead of scikit-learn because it's kind of like there's a new change. Let's go to PYPR, not PYPY. Let's say sklearn, and you will see something like this here. Sklearn package is deprecated, and now we're gonna use skit/learn instead. So I didn't know this before because my scikit-learn package it was installed many years ago, and I saw it because I was teaching this one again. I saw it, and then I immediately searched, the sklearn and the and also pandas. Pandas is here. Pandas, remember the four packages we mentioned in the end of tutorial number 2? We've mentioned here. And these four things, NumPy, Pandas, Matplotlib, and this sklearn, these things we will learn, frequently learn in this course in this semester. Okay, so this is how to fix the issue. Once this issue is fixed, you see there's no kind of error anymore, so that I can run it. I can simply just, sorry, the keyboard. Okay, so I can run it. So this is clearly, so I can have M, I can for example print M. And then let me run it here. So M is 1, 2, 3. And this is a special things called array. Later we'll see a lot. So this is about the NumPy here. Let's review a little bit about lecture number 4. I know that's in the last class I stopped here. Oh, by the way, I would like to mention this thing again. Sorry about it. About for example, all the lectures gonna be here in the folder, and also the record in case you have questions or in case you missed the class, you can find everything here. So I have all the YouTube links. So I believe I set it to be public so that like this one is the last class, so you can see everything. In case you have any questions or something, let me know, because before I know a problem is the font in the pie chart is too small, so I set it to be a bit bigger. Just if you have any questions, just let me know. Okay. So let me repeat, have a review of the motivation and the idea of linear regression here. Again, this is really, really too important. Okay, so basically we have these blue points are our observed data. To make my life easy, I assume it is 2D. In the real application, you can have millions of dimensions, but here assume it's 2D, so I can plot. I see that it has a linear trend, and I want to figure out a line. Why a line? Because linear trend means linear function. Again, assuming here's 2D, in a 2D, a linear function is a line. In a 3D, a linear function means a plane. So I want to find a line to fit this. But I have infinitively many choices. So which one shall I choose? We always want to choose the one has the smallest error, but I mentioned error. I need to define what does error mean, because here it's kind of like mathematics. I need to define everything accurately. So we define error as the least square linear, as a least square error. So why do we need to define least square error? Because usually when we say error, we will mention about absolute value, but absolute value later, we will choose to minimize the RSS, which is optimization. Absolute value in optimization is very difficult to be handled, and hence we make it to be square. Instead of considering this absolute of yi minus yi hat, I consider yi minus yi hat square. And this will make a quadratic function, and in optimization, it's going to be very, very easy to be handled. And hence, I consider for data I observe xi, and the yi is the true data that I will see. And the yi hat is the projection of this data onto this line. In other words, suppose I have, I believe I have here. Let me write it here. And so, okay, let me choose the number data color to be, let's say, red color. Suppose I already know the f. So how to get to the yi hat? I can say yi hat equal to xi. So this xi is I wrote xi hat because in case there are multiple dimensions, it's a xi hat vector. This is something I observe it, and the f is something I want to get. Suppose I already have f, so I can have the predicted data, predicted response for data xi. I name it to be yi. So this is the thing. So by our observation, we actually have xi and yi, no hat, okay? No hat, this means the actual observation. And the yi hat, which is here, so this is yi hat. This is the true observation yi. Y hat means the predicted data, which means the projection of my xi onto this line. Suppose I know f, so I have this y hat. So I just need to calculate the actual data minus the predicted data, square it. So this is the square error of data I. But the truth is that I have n observations from data 1, data 2, blah, 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 till data n. How to calculate, how to check them? So we calculate the summation of all the square errors. And hence we have the term RSS, meaning the sum of squares of residuals, or the sum of squares of error. It doesn't matter. Residual means yi minus y hat square, y minus y hat absolute value. And here we go. So in order to have the best fit here, we define the parameters such that this RSS is minimized. And so this is the point. So this is the point of the least square regression. And to make a more clear notation, I have x1 hat. This means the vector equal to this, xn equal to this. And I want to find this f, which is a linear function, which is beta 0. If we write this form instead of matrix form, it's going to be beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p xp. Let me first give you a very clear example here. So first of all, you can download the data here. This is a CSV, I believe. Let me see. How can I see the information? File information details. This should be CSV. Yes, CSV. So I already downloaded here. So let me just open it. So what we are talking about the meanings here. So you can see this column, the Y column, right? So I have a Y1, Y2 until I believe 100 observations, Y100. So this is it. And you see here, my X vector has 6 attributes, meaning my X has 6 dimensions. So this is X11, X12, X13 until X1 100. And similarly, here's X21, X22, X23 until X2 100. And do the same thing for X61, X62 until X6 100. So this is the same. Okay, now we have, well, I have another one, so I can close. Now we have these axes. All these are observed data, and the Y here is also the observed, no hat, okay? But I want to find Y hat. This is what I want to find. In other words, what I want to find are these beta 0, beta 1, beta 2 till beta p. In this example, since we have 6 dimensions, so I have beta 0, beta 1, beta 2 till beta 6, okay? So this is the thing. As long as I figure out the beta, I figure out this f. And hence, I just need to substitute my observed x inside so I can get the corresponding y I hat. So this is the thing. Okay, now, one thing I need to clarify here. Here, xi till xp, it is again just the dimensions, okay? When I say the ith data means the vector, which is xi1, xi2, blah, blah, xip. So this is the notations. Okay, so this slides basically introduce the same thing. Suppose I already know f in the meaning of I already know f means I already know this beta vector and the beta 0. So I can simply just substitute each observed xi inside, so I have the corresponding yi hat. Again, hat means the fitted or predicted data, while the yi without hat means the actual observation. Okay, now following our idea here, I want to have my RSS to be minimized. First of all, I need to explicitly show what is the RSS. So I have yi is this one, yi hat is what? Is this, right? So I substitute inside, so I have, let me make it thing here. Here. So I have yi minus yi hat equal to this. This is nothing, you just substitute, the expressions here inside, so you get this. Now, your RSS means the summation of all the data. So you just put a sigma, what that means here. You just put let me use another color. You just put a sigma here. Well, why still this color? Sorry about it. Let me delete it. You just put a sigma here, and everything's the same. In other words, we want to have what? We want to have find the beta in the beta 0 such that this one is the RSS here. This one is minimized. Okay, so this is our thing. Okay, now it's going to be an optimization problem. I assume everybody has learned calculus, like a calc 1, calc 2, calc 3. So everything should be pretty simple. Before that, let me first define the matrix form of the model. So again, we have this yi, have this beta 0 plus beta hat transpose and x2. This notation is transpose, okay, because by default, a vector is defined as a column vector. Transpose it makes it to be a row vector times column vector, make it a scalar. Okay, so everything is scalar plus scalar. So I can actually write all this to be this extremely simple form, which is the y hat vector equals to x matrix times beta. But be very, very, very careful of the definition of my x and beta. So y hat is still the prediction vector, which is hat y1 hat until yn hat. Here I assume I've observed n data. And remember, for each x, what is the dimension? It is p, right? But I will define my x here to be, n by p plus 1 dimension. N means n rows corresponding to the n data, observed data. P plus 1 instead of p. Why? Because I will have my first column always to be 1, 1, 1, 1, 1. But why do you need to define in this way? Why don't you just define, for example, x to be like this one? So it's going to be n by p, which is just my observed data. Extremely simple, right? The reasons because in my beta 0, I have in my beta vector for beta 0, in order to make the form to be compact. In other words, I want to absorb this beta 0 into beta vector. I will have to make the dimensions, balanced. Otherwise, like n by p, you cannot use n by p minus multiple n p plus 1 by 1. Matrix multiplication cannot be defined like this way. In order to make x, multiple beta, I need to make this dimension equal to this dimension, right? This is the definition of the matrix multiplication. And hence, I need to make them to be equal. And again, by matrix multiplication, remember how to do matrix multiplication. I want to make x times b to be equal to this one. I need to make what? I need to have for each data, I need to have a beta 0 here. And hence, I have a 1 here. So for example, consider the first row times beta is what? Isn't it 1 times beta 0 plus x11 times beta 1 plus x12 times beta 2, blah, 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 plus x1p times beta p. Isn't it the same here? So this is the reason why I need to increase, I'll need to add a 1 column here. The meaning is to really just to make this one equal to be this one. That's it. So that's why I need to construct a 1 column here. And similarly, I need to absorb this beta 0 into the beta vector, and hence this beta vector is p plus 1 times 1, okay? The plus 1 is from here. Similarly here, n row is the n observation, p plus 1 is from here, the first column, okay? So this is my notations. And now we can do some interesting optimization thing. Sorry about it. Here, let me see. Okay, so here I basically showed an example. So consider, suppose my beta, my x has 2 dimensions, x1 and x2. Here, I use it to be x dot 1, x dot 2, but the notations is actually here just x1, x2. I wrote the dot just, just to make it more, make it clear that, it is going to be the 2 dimensions here. And then I have y hat equal to x beta. So I have y hat is, I didn't show the y hat here, but for this x, it is what? First of all, your first column is always 1, 1, 1, 1. Everything's just 1 column. And the rest of your x matrix is nothing, just copy and paste. You can see it's just from here. It's just from here. And then just copy and paste to here. So this is the rest of the x matrix. Beta, because I have 2 dimensions, so the beta gonna be beta 0, beta 1, beta 2, where this beta 0 is again the what? The intersection part, the beta 0 here. Okay, now the problem is how can I find the beta vector and beta 0 to minimize this? Again, LSLR, these square linear regression parameters are nothing but the beta vector and the beta 0, because as long as based on the form here, as long as I know beta 0 and the beta 1, I know the f. As long as I know the f, I know the y hat, so I can calculate everything. But the thing is, how can I get it? Okay, now, still remember the method of Lagrange multipliers. Again, I assume everybody has learned Calc 2 and Calc 3. I believe this should be in Calc 2 in most textbooks. So, consider an unconstrained optimization problem to minimize f where the parameter is beta, variable is beta. The necessary condition of the optimal solution is what? The nebula is nothing, just the gradient. The gradient of the f equal to 0, right? Which means if you expand it, it's going to be partial f partial beta 0 equal to partial f partial beta 1, blah, 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 until partial f partial beta p, everything equal to 0. So this is in general, this is a necessary condition. But if f is a convex function, then this condition becomes both necessary and sufficient. As a special case, a quadratic function is a convex function. Remember, convex function means, it's gonna be the Hessian matrix. And basically, the Hessian matrix must be PD, positive definite. But it's a lot of mathematics. I don't want to expand this because it's gonna, be another maybe 1 hour to at least 30 minutes to handle this. I'm not sure whether I have these things here. Oh, I probably didn't. Let me see here. I believe I have extensive reading here. Let me see. Did I include the Hessian matrix here? I may or may not. I'm not pretty sure. A trace here. No, it's not here. But if you want to see more, what does a convex function mean? You can simply search it. So the most common definition is the Hessian matrix as positive definite. So it's a convex, strictly convex function, or PSD semi-definite, that's a convex function. So quadratic function is indeed a convex function. This is a fact. It's just like x squared is convex, and hence this condition, the Lagrange condition, becomes both sufficient and necessary. And then my life is easy. What I need to do is I just make it a gradient, make it to be 0, and then look at here. So first of all, I have beta 0. I have so this is the RSS is here. Let me just. The RSS is here. Okay, so the variables are beta 0, beta 1 until beta p. Again, yi and xij are known. Okay, these are known data. Okay, so my beta 0 till beta p are the variables. So I first get, okay, what is my RSS, partial beta 0? So this is extremely simple. You have a negative and 2, put a negative 2 here. All other things just copy paste, and then we just, it's just like y equal to x squared. What is the derivative? It's 2x, right? This is I assume everybody knows how to calculate this. Then I will calculate the partial RSS, partial beta j. So beta j is j not equal to 0. Okay, j is equal to 1 to p. Similar here, right? But be careful here. You have a coefficient xij. You see what I mean? And because you have a summation here, you're going to keep a summation here. And you also have a negative 2 from your exponential here. So you will get negative 2 here. You still copy and paste sigma I equal to 1 to n, and then you have an xij here. And after this, everything just copy and paste. So you have this, right? And then just organize the form a little bit. This is very simple mathematics. You will have these equations. This is called normal equations. So basically you want to solve the beta 0 till beta 0, beta 1 till beta p. You want to solve it. And how many equations I have? I have one equation here and a p equations here. In other words, I totally have p plus 1 equations. How many variables you have? You have beta 0, beta 1 till beta p. So you also have p plus 1 variables. In other words, I'm trying to, just solve p plus 1 variables under p plus 1 equations. So using very basic linear algebra, as long as what? As long as some conditions, it's like x. Let me maybe I should write it. Let me use a Microsoft Word here. Let me first clear everything here. Where's my Microsoft Word? Is here. Okay. So it's just like, it's kind of like solving this ax equal to b. Remember this? Everybody, and they want to solve x, right? But here it's a bit different. It's going to be x beta equal to let me call it b, or b is something like the right hand side, something like this. So as long as some conditions satisfied, then we can solve it. So this is basically how we get the solution. And use RSS form, we can easily get the beta. Use a matrix form, we can easily get a beta. So first of all, I need to rewrite RSS to be the matrix form. Here I use the norm notations. By definition, the norm notations means, here's a definition of the norm, two norm notations. And so because my y hat equal to what? My y hat equal to xb, so beta, so that I have this norm equal to y minus x beta. And then this norm can be returned as this. I mean, this is, the same thing, just scalar like a quadratic. And by this one, I just make the lambda of the beta. And this is also extremely simple because remember, in derivative, like if I want to get, let me make it like this way. If I want to make the derivative of fx and the gx derivative, how to get it? With respect to x, of course, suppose, on x. Then I'm gonna have what? I'm gonna have fx, f prime x, gx plus g prime, let's say fx, g prime x, right? I mean, this is the very basic derivative. Okay, so now let's have a look at the form here. Our form here, our form here is this. It is this one. Where's my notation here? Line. Okay, let me plot a line here. So this is my form. So how can I get the derivative with respect to beta? Similar. So first of all, you have what? You have a negative x t. Be careful. Here's a t with respect to beta. So I have negative. Oh, sorry. I have negative x t. And then you copy and paste this part, y minus x beta, and everything's bold because they're matrix and or vectors. Okay, now you copy this part and see this part. This part, you see what? If you get a derivative with respect to beta, you got another x, right? But be very, very careful. You cannot write a negative, this t, negative x. Why? Because in terms of dimension, it's wrong. So you should consider to fit a dimension, you will have the same thing, which is the whole thing of the t, which is x t y minus x beta. Again, to make everything to be bold. Okay, and you find what this thing is what, and the two parts are equivalent. See it? So that it's going to be nothing but a -2 of this. So this is how we get it. And this one by the Lagrange condition, because here is quadratic, which is a convex function. So this should be equal to 0. This is necessary, and both necessary and a sufficient condition for my optimal solution. And hence this equal to 1. And then you can see this is too easy to be solved, right? This is, so I get what? I get x t y minus x t x beta equal to 0. Again, make everything to be bold. And then I want to solve beta. And I'm asking you, hey, what is beta? 0 vector. And this one, guess what? I get beta equals to what? Equal to this. X t x, you see? I can move this part to the right side. So this part inverse. And then x t y. Make this. These things not to be bold, just the format things. Okay, and this is my solution. Yeah, this is correct. And the reason I put a hat, is because it's just a notation, just to tell people, to indicate that this beta is an estimated parameter. And this is called the OLS estimator. But here, from my steps, didn't you find a problem? That I directly from here, I claim I have this one. The thing is, I need to guarantee that this one is inversible, right? Be careful for a matrix. It doesn't mean the inverse matrix exists, okay? I mean, again, regarding this, it's going to be a lot of things. And then what if the inverse doesn't exist? Then you're going to have the pseudo-inverse, and you have 3 forms of the pseudo-inverse matrix. But these things are all some other story. It's gonna take a long time to explain again. I'm just gonna ignore it. Here, suppose we just assume that the inverse of xtx exists. We assume it. Okay. So I believe I must have written something here. So one can clearly see that using the matrix form, it's much easier to get this. And we do need to assume the inverse exists. In other words, x is over 4 rank. Otherwise, something gonna be really, really wrong. Okay, so now let's have a look at the example that, the example. I just make a fake baby example here. So let's have a look at it here. So again, my X matrix equals to what? Let me write it down here. Sorry about this. So now considering this example, let me use another page to make my life more clear. So now I have Y equal to what? Let me see how to, I wish I can have directly use the latex, make my life easier. Let me see here. Let me make it bigger. Sorry about it. My Y equals to, and then 3. Okay, so my Y equal to negative 1.03, 3.99. So I'm talking about this. Okay, and then 7.63. This is my Y vector. Okay, how about my X matrix? X equal to, so I'll have a matrix here. Be careful, X is going to be 3 by 3 instead of 3 by 2. Why? Again, the first column is always 1. Everything's 1, okay? And now I just copy and paste everything. 1, 3, 2, negative 1, 0, 2. Okay, so this is my X, right? Okay, now remember, we just get at beta equals to what? So first of all, let me just add a notation. Just because it's the very first time I use this notation, I just want to make it. I would like to write one more step. At beta 0. Sorry. Copy. This keyboard. Anyway, so small. Beta 2, beta 1. You might ask me why it's beta 0, beta 2, beta 1. Beta 0 is always there, intersection, but the beta 1 and the beta 0 is because I have 2 dimensions, and hence I have beta 1 and beta 0. Remember, if we go back here, you're gonna see it? The number of beta always equal to the dimension of your X. Your X here is 2D, and hence I have 2 betas here. Okay. And this equal to what? Equal to this. Sorry about this. I'm just pretty lazy. Let me copy and paste. Equals to this. And then you can simply just calculate everything. You know what I mean? And so you can calculate beta. And here I do have, sorry, I don't have MATLAB here, but I have this one. The Octave. So Octave, I call it a free version of the MATLAB. So I have let me see here. So I can easily calculate the matrix. Anyway, let me what is the numbers here? So my Y's are like, okay, so my Y equal to and then my X equal to X equal to the last number, what other number? 2, 2. Okay, so this is my X. So now I want to have my beta equals to, remember the formula here? Xt, X inverse, and xty, okay? So inverse of xt, x, and then, sorry, you need to make a times xt times y. What happened? Okay, sorry, my fault. You see what I mean? I forgot a 111 in the beginning, and that's why it's something wrong. Let me see, x equal to 1, 3, x. Okay, One fault. My fault. My fault. Should be 1, so 1, 3, and 1. So I will manually manually include it. Okay, so this is my x. Now I can do the same thing again. Why still wrong? Let me see. This should be I get confused here. Ah, I know why. Sorry about it. Let me redefine one. Why should it be a column vector instead of row vector? I define it to be a row vector. So now y is column vector. Now hope everything is correct. Okay, so now this is the solution. This should be the same as what we calculated here. Yeah. So this is the solution of my least square error. And now I can calculate, you know what? I can calculate the y hat, right? So this is the residual of the error. So it's going to be y minus x beta hat. So what does it mean? So this y is the y that I see, which is which is just this one. This y is just this y, the same thing. And x hat, x is this is x, the matrix x, and the beta hat is this one. In other words, this x minus, this x beta hat means what? Means this is the y hat, because that's my definition. Remember our definition here, our matrix form. Here we go. Sorry about this drawing. Y hat equal to x beta. So now I've already calculated the beta, or let's call the beta hat to indicate it's some fitted parameters. X beta hat is a y hat, and this one will give me the y hat, and we can simply just just run it. Y hat, let me see, y hat equal to x times beta, and then I have e equal to y minus y hat. Here we go. And you can see these numbers are extremely small, almost 0. Well, a little different must because of rounding things. Y is almost 0 and y is extremely small, to be honest with you, because I cheated. I actually made this number from a linear function, just add a very small error. That's why it's like this way. In the real life, you want to see it like this. Okay, I remember I just, I cheated the numbers. So, I make the fake numbers, and that's the result. Okay. The problem is, well, suppose you have you figure out a beta hat, so you know a linear function, but you want to evaluate, hey, how good is the quality or the fitting, right? So we have actually many methods, and one of the most popular method is using R square, which is the coefficient of the determination. So the R square is defined by this formula. It's 1 minus RSS over SS total. RSS is the one that we just mentioned here. This is the RSS, and the S total is, so RSS can be easily calculated like this way: y minus y hat square. And then so for example here, I can say norm of E. So this is the RSS. Of course, here's extremely small. Again, because I just cheated here. And then RSS is defined by this, where here y hat is the average of y. In other words, it is every time I use the y minus this y hat and then get a norm. Or you can just, all the definitions here. So you can easily get S total. And then you have the S total, and then you have the what RSS. Then you get to the R square. By the way, S total is not related with the your linear regression, because it doesn't need anything other than yi. You just need a yi, so you get everything, and then you get R square. Then we are not gonna code it in Python manually. If you would like, it's a very good kind of like homework you can consider it, because really everything's so direct and simple. You just you know the x, you know the y. You need to use a numpy to do those kind of matrix multiplication. Later we'll see how to do it in Python. But here, to save the time, because this is really a very simple work, I will introduce directly use the package. So here we're gonna use Jupyter Notebook. I remember last time Cole asked a very good question, which is why do you need to use PyCharm instead of Jupyter Notebook? So first of all, let me introduce a little bit what is Jupyter Notebook, in case other students may not know what is that. So Jupyter Notebook is something developed by Jupyter under the platform called Anaconda I hope everyone has already installed it. Anaconda Navigator is here. In the last class, I asked everyone to install it before today's class. So it provides you a lot of existing packages. Remember, here in the PyCharm, we got confused about interpreter and also about how to add different packages. But here, if you use the NumPy, sorry, if you use the Jupyter notebook, you don't have to use include everything again, add install the packages again because it's based on the Anaconda, the Anaconda platform in which a lot of packages already, are already included. The second thing is Jupyter Notebook is a very, very simple form, provides a very simple environment for coding Python things. It's based on cells, while PyCharm is something like, provide a more general like platform for a bigger project. So let's first have a look at the Jupyter notebook. So let me just open it. So I just need to open Anaconda Navigator. Wait a little bit. Okay. Open. Okay, so Jupyter Notebook is here. I just click launch. Depends on your browser. It will just, kind of like a browser oriented, like, a web page here. It will open. So my browser is Google Chrome. So I use Google Chrome. So here I can create a new, let me create a new folder first. I can call it 2024 USA CPE 46 in class. So this tells me that, okay, this is this course and this is in class. And then I can open this folder and I can create a new notebook. Okay, so it's going to ask you what kernel will you use. So here's because it's from Anaconda Navigator. So I just use Python 3 PyKernel, and it's basically here. The kernel is gonna the environment is gonna be around here. So the base root, this is the Anaconda environment. So it of course includes everything. So to save my life, I click always start the preferred kernel, so select. And then here I can change my name to be lecture 4 linear regression 1. Rename. Oh, okay. So it cannot have the column. Lecture 4 underline linear regression 1. Here we go. Okay, so I've renamed it. So you can see, so suppose I just close it. So it's gonna be well, it should be here. Okay, I just refresh it. So it's here. And then in your document, I believe here, because my OS system is a Windows system, I believe it's in the user under users. So this is my username. And then it should be yeah, it's here, you see. So by default, I mean unless you change the path where to install Anaconda, so by default, those kind of things gonna be around here. So you can see. And this is .ipynb. That's the Jupyter notebook. So that's the thing. Okay, now let's just in case, later if you do homework or if you write a lot of things and you cannot find it, say, hey, what hell? I did so much work and where is it? I cannot find it. So it's right here. Okay. I believe now in the new version of Jupyter Notebook, they have some very good functions, which is I believe you can download it. Let me see. Because when I used it many years ago, you cannot even download it. I let me see, where can I? I'm not sure. There are some places you should be able to download the things. Code, no. Let me see, edit. You can simply search, but I'm pretty sure I saw it somewhere that you can download the code. So it's gonna make your life much easier instead of just trying to find it, in your local drive. Okay, so now let's have a look at what is the Jupyter Notebook. So you can see here. Let me open Chrome. So each of these is called a cell. And then a cell has two modes, which is edit mode versus command mode here. And basically, how to switch between two modes, you just press escape. So let's say I can do whatever. Let me see, where's my here. I can do whatever I want, and I press escape. You see it? because before you can see here is blue at the press escape, it's dark. Now I can, for example, add another cell. Let's say I press B, it's going to be another cell. I can do whatever I like again. So, and we can run Python here. Suppose I say t equal to 1. And then I can click this one to run or to make your life easier, Shift plus Enter in PC. So I push Shift Enter, so run it. So I can put it like this way. So in this case, whatever I run, the result will be immediate here. And then I have another cell. I can still say t plus t equal to t plus 2. Then I put a t. Okay, it's sorry, t equal to t plus 1, so that it's gonna be 2. So what's the difference between this one and the PyCharm IDE? No essential difference, but the thing is here it's like an environment of a notebook, so it makes things easier. You can immediately see the result, in the result together with your code here. Remember in PyCharm, it's gonna be in the console. It's you have to kind of like, you cannot, let's say, run a thing here and in another cell run another thing, in the third cell run the third thing, like simultaneously, and see everything together. It's more convenient in a notebook. For a small project or something, notebook will be, definitely our first choice. It's just, more convenient, more concise. So that's the thing. However, be careful of one thing, that these cells, the relationship of these cells are dependent. So, but to make them dependent, you need to run a cell first. Let's say here, suppose I write s equal to 2. And then I didn't run it, okay? Be careful. So now here I directly say s plus equal to 1. And now I say s. You will see an error. Why? It shows s is not defined. You may ask, hey, I defined s here. Why it shows not defined? Because you wrote it, but you didn't run it. You know what I mean? So I will have to run it, Shift Enter, okay, or I press just this button, run it. Now I run this s, it will tell me s equal to 3. You see what I mean? So this is the thing. Or you can use your printf function. Print f function. Okay, one more thing, sorry about it. To make your life easier, you can view here, show line numbers. So it will show the line numbers here. Another thing I would like to do is, let me see here, auto close brackets. This is great for lazy people like me. So now you just need to press 1. It will, or also quotations, it will appear together. This fit people like me. Another thing, if you would like, let me see, now Jupyter Notebook, it has a lot of interesting themes. So somewhat this is even better. I don't know which one you like. For me, this is kind of better, but in the slides, the reason I use white, because I don't know whether you would like to print it, because if you want to print it, then definitely white background would be the best. Otherwise, it will waste a lot of ink. So so that's the thing. Okay, so here you will need to run this, then it will be there. And later we will see that usually for import NumPy, import matplotlib something in the first cell. After it, as long as I run it, I don't need to in every cell, load it again. So that's the thing. And I believe I showed some examples here because these things are extremely simple. So I'm not gonna print it again. So you do whatever you did it like in PyCharm. Like you can define a function, you can define a class. In the class, you define the functions of the class, and then you just do all those things the same thing. Just introduce, print. Everything is exactly the same. The good thing is that, you know what I mean, you can immediately see the result here, in the same kind of like window, instead of like in Python, when you run this code. When you run the second code, the result of the first code cannot be seen simultaneously unless you write everything together, but it's going to be more complex. So this is the thing. Okay, now let's have a look at the edit mode and the command mode. As I just mentioned, when you're writing, let me see, when you're writing the code, you just press escape. Then it's going to be command mode. In the command mode, you can have, so here you can go to help, show keyboard shortcuts, help, show keyboard shortcuts. So you will see all those kind of shortcuts. And specifically, here, several things are extremely important that you're going to use every day. The first one is, sorry, it should be, I believe Shift Enter. That's interesting. I realized that actually for control enter it also works. Yeah, I usually use I don't know why it shows run this cell in advance. Okay, here I believe run the current cell as control. Okay, run selected and do not advance. This is control enter. And the shift enter is run the all the cells and advance. So this is the shift enter. For myself, I usually use alt control enter more than shift enter. And then A means insert a new cell above the current cell, B is below, and DD is delete. Okay, so let's test these three first. So shift enter or control enter we've already seen here. Then suppose I select this one, I press escape. Now it's a command. The command mode is then I press A. You see, it insert a cell above it. Or if I press this one, escape, and I press DD, it will delete it. DD, delete it. Or I press this one, I press B, which is insert a new cell below. So you can insert as many as you want, and just delete all of this. So these are the three things that we use the most. Use four things use the most. Later when we write code, we will see that we use a lot for tab or shift tab. Or let's say if your memory is extremely good, then you don't need this. For me, my memory is not that good, so it will give you some hint of a function or something, so that you can always check tab or shift tab. So these are the things, and these are the thing. This thing is the thing I just showed the line numbers. And this is, by the way, something about markdown here. So here, by default, it's code. You can make it to be markdown. So for example, you can say, oops, add, then run it. It will be like this way. And the good thing is nowadays it already have, I believe, markdown reference. Before Jupyter Notebook doesn't have it, and I created this one. It's from I believe I stole it from IBM, I believe. Let me see. Yeah, it's from IBM. It's kind of like a Jupyter Notebook cheat sheet. You know, if you're interested, especially when you do homework something, you can write something like homework one, something like from Paul. Let's say problem one. You can do like this, and then add something below, and then problem two, sorry. And then make it to mark it down and then run it. Problem two, and then here in the command mode, you could just B and then either write whatever code problem three. You can do it like this way. But good thing is they do have the reference here, so markdown reference. You don't have to go steal something from IBM. You can directly get it from a Jupyter Notebook. So everything's here, like italic, bold, heading. Everything's here. So okay, but our focus here. Let me delete all of this. Our focus here is not these things. Our focus here is how to use Jupyter Notebook to run the basic linear regression. Okay, so now I'm going to import two things, which is pandas and NumPy. Again, pandas is something like Excel. You're going to handle something like a data frame, use pandas. NumPy is kind of like more like MATLAB, those kind of matrix related array, those kind of things. And then let's try to let's first do this one here. Let me see, where's my, oh, sorry. Okay, so let me just, so I'm gonna import pandas as PD, import NumPy as MP. By the way, I mean this PD and MP are just those kind of notation. You don't have to call it PD. You can call it PD 1, 2, 3. It doesn't matter. But like a habit, I always use those kind of things to be PD and MP. And then I'm not sure why it's show the error. Sorry about it. Sorry about this. That's something I use. Let me see. How can I grammar? Okay, here we go. How can I turn it off? Yes, for the session, turn it off. Sorry about it. And then I will need to include a path. From this path, I will read the data. So path equal to, here I have a R, this R parameter. This R word shows you kind of like absolute, citation. And I need to find the data. So again, this data is here. So I downloaded to this path. lecture 4. So here I just, this is data, I just copy and paste everything here. Where's my Jupyter? This slash, and then the name is, I believe it's 60. Yeah, it should be CSV. Yes, CSV dot CSV. So this is my data, and I can read the data. I run it. How come this is wrong? Not defined. Sorry. I even didn't read it. PD dot read CSV, I believe. So here, if you're not familiar, you can just, you see here how I get it. So PD dot, I press tab. I press tab, it will give me the hint, So let's say, suppose I forget the details. So you can see it's read underline CSV instead of read CSV. So I know it, I press enter. Let's say C, and then here, press enter CSV, and then pass. Now I have to define the data. I can read the data. So here's the data. Of course, if you're lazy, you can just, here I already opened it. You can just directly, suppose you installed Excel. So then you can just open it in Excel. So you can see they're just exactly the same thing. 100 rows, 7 columns. So this is how I can read the data, define the path, and then data. Okay, now the next thing I want to do is I want to get the X data and I want to get the Y data, right? Okay, so now here is kind of like in scikit-learn, later we will use a scikit-learn. Remember we just mentioned when we define X matrix, mathematically in the matrix form, we need to add this, right? Okay, now in scikit-learn, the package, it tries to make the life easier for a human so that in their X, you don't have to manually add this one column anymore. So when you're doing mathematics as a matrix form, you need to know X is this. But when you're running the code, you just need to input this part there. So here, what I'm gonna have is, where it is? What I'm gonna have is, so I'm not gonna read the whole thing as X. I will drop the first column, which is a Y column. So I can write a thing like this way. I will have, let me see, where's my, so now I can insert another one below, another cell. I can write it to be 1x equal to data dot job. So here I can just simply write columns equals to Y, because here I know the name is Y. You see, columns equal to Y, and axis equal to 1. So axis equal to 1 means drop a column. Equal to 0 means drop a row. And then I can just read X. And you can see, indeed, X is dropped to Y. So we have, wait a minute. Okay, in the slides here, I'll use another method, which is the data dot columns 0. So similar thing, which means it tells you, hey, you're gonna drop what? Drop the 0th column. Be careful, the index starts from 0, not 1. So it's gonna drop the 0th column, which is the Y column as well. Or you can correspondingly write like this way. I'm just pretty lazy, so I write like this way. The reason I give this one, sometimes you want to drop several columns. Let's say, suppose you want to drop the 0th column and the 2nd column, so that you can just write, make it to be a list object inside, make it to be 0, 2, or here I show the 0, 1. It doesn't matter. You can do it like this way. Okay, so let me see here. So we have seen, so once I write X like equal to data.job, and then so the first X, so the first Y column is jobbed, and then X equal to this. Be careful of one thing, that here job won't really make the things to anything to data. It won't change the data. So for example, suppose now you want to see, hey, what does data look like? You see, in data, Y is still there. So this is job a method that won't really change the original, variable data frame data here. It just shows you how I can define my X here. And then similarly, I can define Y. So I'm gonna have, let's say, Y equals to data. Y. And you can see Y. What does Y look like? Y looks like this. And you can see it's, excuse me, it's exactly, this 12.294. You see it? It's exactly this. Or you can use the method that I showed in the slides as well. Just because I'm lazy, so I never write it like this way. In case you have several responses, something, you'd better use this one, because in this one you can put, a list here, and you can, like what we did here, you can include the multiple columns. Later in classification in this class, you will see some examples here. So now I have what? I have X, I have Y. So I need to do what? I need to train the data, right? Okay. So here we need to have three types of data sets in machine learning: training data, validation data, and test data. And the details will be given in lecture 6 or 7, 6, I believe. I will show like cross-validation, how to include the validation things here. But at the current stage, you just need to know the training, validation, test. And usually in scikit-learn, we basically just use training and the test, because it's kind of a pretty pretty lazy, because otherwise later we'll see you will separate the text data to be tested, the test data to be tested, the real test data and the validation data. But we will see everything later. So basically the training data, as a name, we will use this part of the data to train. The validation data is to tune the hyperparameters. Here you may get confused. What does hyperparameter mean? Later, for example, in KN and some classification data, classification methods will mention the validation methods. The most widely used are these two methods: cross validation and bootstrap. The good thing is that you don't need to manually write it. In this kind of modern packages, everything. Excuse me, sorry about it. In modern packages, everything's gonna already be coded, and you can simply use. And the test data is something to provide a final check to the model. You want to see, hey, how good or how bad the training result it is. Say, for example, suppose here we have 100 data. So usually later in the code, you will see we will separate it to be 70 data for training, and 30 data for validate for test. For the test. And here, temporarily, we ignore the validation data, but in a more formal method, you're gonna use the validation data. You will see it in the later lecture. Let's have a look at here. How can I really use these things to run the linear regression? To make it, more clear, I just insert another cell here. So here I'm just, separating each part. Each part we're gonna be in a cell. So here I'm gonna have import scikit-learn here, and then I will have from sklearn import linear model, linear linear slash model, I guess. Let me have a look at it here. Yes, an underline, not slash, linear underline model. Here, you may ask me, so why don't you press tab? Yes, I did. The thing is, it takes some time, and that's why, sometimes when you import, it's not going to be so good, but later it will be great. Then I will have X train, X test, Y train, Y test. So I will use these four matrix. X train, X test are matrices, Y train and Y test are vectors to store the training and the test data. sklearn dot model, and I can press the tab here. I know it's model selection dot train test split should be, yes, train test split. Okay, here we go. And now suppose you forget, how about, the keywords here? You can press shift and the tab, and let's go. Hey, come on, shift and tab. Okay, it doesn't show again, probably because it takes time, because scikit-learn is, a relatively big library, but basically the keywords are X, Y, and the last thing is a ratio, which is how big you want the test size be. I want to say test size equal to 0.3. That means I would have, let's say, 30% of the data for test, and the remaining 70% for training. So I will have 30% testing data and the 70% to be the training data. So after it, what I'm gonna do is I'm gonna print, let's say I want to have a look at it on a print X train. Did I? Let me, it don't matter. Y train. I will have a look at it first. Uh-oh, sorry, what is wrong? Number scikit-learn import linear model. Oh, scikit-learn wrongly spelled. Scikit-learn ERN. That's why just now I pressed the tab, the tab key. It doesn't. Let me see if I press tab key. Yes, here we go. So linear model. You see what I mean? That's why sometimes it's okay. Now let me see it. Okay, so you can see this is the training data, and indeed you see the numbers here. It's just a randomly. It doesn't just randomly choose. It will have 70 rows times 6 columns. So this is training X train, Y train, and the Y is the same. You see, length is 70. This means I'm gonna randomly choose, let's say, 70 X's and their corresponding Y's for training, and the remaining 30%, which is the test size here, is gonna be for testing. So here, I believe, let me ask you a question. So why do I need to make it like this way? It's kind of so complicated. Why don't I just write this? This means I'm gonna take the first 70 data for training and the last 30 data for testing. Isn't it simpler? Why do I need to write, like this way? Why do I need to randomly choose? This is because, be careful, in some cases, in many cases, actually, if you write this way, your training could be very, very biased. And even later, may see something like overfitting. Because just in case your data follows some order that you may not know, for example, like time or whatever order, suppose you don't know it. Okay, if you know it, you will have sequential fitting. That's another thing. But suppose you don't know it, you doubt what if it has some whatever order that you don't know, then using a random sample to train the data will be much, much better than you just brutally say, okay, only the first 70 for training, the last 70 for 30. So this is kind of like a common kind of like a common sense. Usually we want to select randomly select training or test data instead of assigning this. Okay, so after this, here you can see the test data as well. So I just need to make this one to be tested. Okay, so here's the testing data, and indeed, the length. Indeed, you can actually, if you want, you can count the length of this. It's 30. You can see the length is 30. And it's the same thing for the Y. So this already from this we already get to the test and train data for axis and for X and Y's. The next step is to fit the model. Let me just add one more cell below. So I'm gonna fit the model. Model equals to linear. Remember, here I already import a linear model. So I have linear model. Dot linear regression. Let me use again, I press the tab, it tells me linear regression. Okay, so here is I tell Python that hey, I'm gonna run the linear regression, and the object is called model MODL. And then I'm gonna say model dot fit. Okay, I'm gonna use X train and the Y train. If you don't know, the keywords, again, you can use it. You can press Shift plus Tab. Oh, great. That always fails. Great. And the Y trains. These are the 70% of the training data remembered. So I can do this. And now I need to see how good or how bad the quality of the fittings. Remember, R2, what is that? The coefficient of determination, which is right here, we define here. This one. But the good thing is everything's already coded, so you don't need to code it again. This equal to model dot score, I believe. Yes, score. And so how do you calculate by what data you need to get the score, right? Okay, so again, I don't know why shift tab doesn't work here, but anyway, it's gonna be X train and Y train. Why? Because these are the things I used for training the model. So the R2 coefficient should be, the R square coefficient should be calculated by this. Okay, this is how I already, the training. As long as I run it, you know, it's going to be trained. But we need to print out the results. So I can say print, let's say I will print the r square equal to, so I can say R2. I've already defined R2, and then I can print, let's say, remember, finally fitting, what does it mean? You need to get to the beta 0, beta 1, beta 2 till here I have 6 data, so I 6 dimensions, so I should have from beta 0 to beta 6, right? So first I will have the interception beta 0 equals to, let's say, model the intercept. Now I will have print the coefficients beta 1, beta 6 are. So here I can have model the coefficient. Yeah, here we go. So as long as I run this, let's run it. It's gonna tell you something. Let me see. It's again train. Okay. Okay, now here we go. We have r squared equal to this result, and then interception beta 0 is this one, and the coefficients are beta 1, beta 2, beta 3, 4, 5, 6. An issue is that you may feel it's kind of like, oh, it's kind of too long, you know, like our human, you know, like the habit. I don't want to, you know, the show things to be so long. So a trick is here. I can make it to be R2. Let's say, suppose I have, let's say 3 float digits. I can write that 3f. And similarly, I can do the same thing for all this. Intercept the same thing. And then here. So now let me see why coordinate format. Let me see here. Okay, so this is an issue because, okay, indeed, here we go. But because this model coefficient is gonna say make it to be array list, I believe I have the mp dot precision set I forgot details, set something. Let me see. Set printing precision or something. Set print options. Dot set print. Again, I pressed tab print options, and then I can have something precision equals to 3. So this is gonna show this array list to be 3 digits. Okay, here we go, 3 digits. So this is how I can make this. And the details of this, you know, about the format here, it's gonna be shown here. And oh, one thing here, because here I kind of like I'm cheating. I know it has 6, you know, dimensions, but I can use this one to show the different things. So for example, I can let me. So here, let me print x train dot shape. So you can see here, I count 76. That tells you that X train, this matrix is 70 rows and 6 columns. So I can say print shape 0 to indicate this 70 or 1 to indicate this 6. Okay, so now I can use this one to avoid my manual like input 6. So I can put this. I'm gonna have X train, X, let's say X dot shape, it doesn't matter train or shape because they're the same thing. Here we go. So in this case, I can automatically recognize what is the dimension of this. So I have already R squared equal to this one, interception this one, and the coefficients beta are this. So this is a very brief introduction of everything. And the last thing I want to do is that I want to have what I want to predict, because I've already had my betas. I've already had my F, and hence I have my Y hat, right? But I want to see how is the Y hat compare. How is the Y hat compare with the true things? So I'm going to use this part to show you the comparison. So I can do like here. And let me just add another cell to do this one here. So here I can have y predict equals to, let's say, model dot predict, and then predict is using x test. So this is nothing but here. You've already had your beta. Let me see here. You've already had your beta. I want to calculate x beta hat, and hence I can get this y hat. So this is the meaning of this step. And then I can have for I in range of length of, let's say, y predict. What I'm going to do is I'm going to print the comparison between the actual and the what? Let's say actual response equals to. So here I have y. Let me see here. I have y test. I'm gonna use the function ilog because ilog is something, you can locate locate the number. So here is the ith number. So I need a y test dot ith number, and let me see here. That's 3f here, and then space versus, or maybe I can write a vs. Predicted response equals to. So now I will have y predict I dot 3f. Let me see. Okay, here we go. So I can see actual response, predicted response, actual response, predicted response. So remember, all before this, I did the things for my training data, and I use my training data. I get x hat beta, x beta hat. I get I get the beta for the training data. I get the beta hat. Now I want to use the thing for my test data to see how good the results are in terms of this 30 test data. So I do like this way. So first I get my y predict. I just substitute this test data for x, and I've already get the beta, so I can definitely get these numbers. And then I'm gonna print for the comparison between actual response versus the predicted response. So here's the thing. And in the next lecture, we will actually show how to visualize the plots here. But here, let me see. Yeah, but here we are gonna just, in lecture number 4, we'll just finish the results here. And as a summary, we can, here we go. So here, I showed the 2 methods, but to be honest, in practice, I use this method more. ILOC will be much easier. Otherwise, you will have to use, so a very easy question is, why do you need to make it to be 2 list? Why don't you directly make it in this way? Because if you directly writing this way, it will be something error. Let me show you something here. Suppose you say, okay, so I don't use the iLock, I just use the y test I, right? Because it looks like y test is something that I've already, I've already got here, which are defined as y test is kind of secondary model selection and a split. Okay, if you do like this way, it will show you an error. Okay, basically the error is that it will make the y test kind of like a format of the, let me see, a format of the data frame. You cannot directly use kind of a y test I. And hence what I did here is I make it to be a y test list, which means I make it a 2 list. So after using this method, then my y test list gonna be a list. And we know for a list, we can use the ith element. We can do this. But to be honest, to save your life, you just use the iloc function, which is much, much easier. So that's what I showed in the class. Let me recover it just. Okay, here we go. And another thing is that when you run this code at your home, you may see the result is different. So for example, here you can see the fitting coefficient is 0.7143. But here, if you see my result, it has 720. You may let me use the 4F. I run it again. You can see that the result is different. Why the result is different? The reason because here, when I make my training data, I randomly choose the 70% of the data for training data. And every time when you run run this one, the selected training data would be different. And hence when you run it in your computer versus when I run it in my computer, the results will be different. Not to mention in two different computers, even in the same computer, you run twice, the results will be different simply because the training model is the training data selections are different. So this is the thing. And then finally, let's make a summarize. Let's make a summary. So we actually run LSLR model in Python following following the 5 steps. Step number 1, loading data. Step number 2, getting the observation matrix X and the corresponding response Y. Number 3, splitting the data into 2 parts, training and the test. Here, because I do not include the validation. Formally, you should have 3 parts of validation. And how to make the validation, which is simple. Let me see, did I write it here? Which is basic, let me see here. Basically, what you need to do is you need to, in the test data, you need to split it for one more part, which is the training and the test and the validation, so that you can make it to be validation. We will see an example in a later lecture here. And the step number 4 is to fit in the model by the training data. Step number 5 to make the prediction on the test data set. So these are the 5 steps, and then we can see, to make everything together. Let me make it. Okay, now let me go to insert one more. So first of all, you will include all those kind of things. And I know that I will import scikit-learn as well. Let me just copy and paste. I'm just lazy. Copy and paste here. Okay. Now step number 1 is what? To load the data, right? So I'm gonna just load the data. Loading the data. What did we do for loading data? We did this, right? And this is just for showing, the data. You don't have to have it. So in the real working environment, you will have this. So step number 2, getting the observation matrix X. Getting observation matrix X and a response vector Y. So how do we do it? We make it here. This is how we get the X and Y, right? And then step number 3 is what? Splitting the data into 2 parts. Here are 2 parts: training and testing data, which is right here. I don't need this 6. Splitting the data into training data set and test data set. Then step number 4, fitting the model by the training data. Okay, fitting model using training data. So how do we fit? We fit it right here. Let me make 2. So here's how I fit the data. And of course, here I printed, the results as well. And finally is what? Finally is to making a prediction on the test data set. So finally is to making prediction. And then what we do here? What predict? So here are the 5 steps. Okay. And indeed, you can see, even if on the same computer, again, you see R square is different, and you can see interception. Everything is very different from the previous results. See it? The previous intersection is this, and by this time is this. Why? Again, because you randomly select 70% of the training data, and hence you make it, of course, the difference. Okay, so that's everything about how to use Jupyter Notebook to run the linear regression. And today we will finish a bit earlier, and that's everything about today's class. In the next class, we'll see how can we visualize all this kind of data in the 2D or 3D, this kind of dimensions. And then we will have a further introduction in lecture 6 about the linear regression. I think that's everything about today's class. Thank you very much. Have a good night. Bye-bye.